In this session, we will discuss about homodyne detection and heterodyne detection. Actually, it is a continuation of the topic from the coherent detection. We have discussed about the coherent detection in the previous video. Now, in the case of coherent detection, there are two detection schemes are available. First one is homodyne detection and heterodyne detection. So first of all, let us see what is homodyne detection. In the case of homodyne detection, actually the optical signal that we have received is demodulated directly to the baseband signal. And in this case, no further demodulation or demodulator circuitry is needed. Actually here, a local oscillator is needed, and in that local oscillator, the frequency produced in the local oscillator frequency should be matched with the carrier signal frequencies that the receiver receives. So, local oscillator is needed and its frequency matches the carrier signal of the signal, and phase of the local oscillator frequency should be locked to the incoming signal. That means there should be a frequency and phase matching in order to achieve the detection process. That means we can write it as omega c equal to omega LO. That means omega c is the carrier frequency of the signals received and omega LO is the localator frequency, localator generated signal frequency. Okay. Here we can write the equation for the detector power by using P of T. Detector power, that is there will be an optical detector at the receiver end, and the received power will be equal to P of T equal to P of PS into PLO plus 2 into root PS PLO cos phi of T into cos theta of T, where PS is the signal power and PLO is the local oscillator power, and phi of T represents the phase difference between the signal power and the local oscillator. Phase difference between the signal power and the local oscillator is generated carrier power. Next, in the case of once this signal is produced and it should be transmitted using different modulation techniques, and the modulation schemes used in the case of homodyne detection are OOK scheme, that means on off shift scheme, that is similar to the amplitude shift keying, and actually it represents the presence or absence of carrier. On means there will be a carrier signal, and off means there will be the absence of the carrier. And in the case of OK modulation scheme, we will vary the signal level PS, where the phase of the signal will be constant. In the case of OK modulation scheme, we will vary the signal level or amplitude level of the signal, but the phase of the signal will be remains constant. In the case of PSK, that means phase shift keying, we will vary the phase of the signal, and we will keep the amplitude of the signal, or PS remains constant, or power of the signal remains constant. And figure shows the fundamental setup of a homodyne receiver. You can see here that there will be the optical signal, and there is a need of phase locked loop that is shown here, and this phase locked loop will produce a carrier signals which is in lock with the optical signal. That means frequency and phase should be matched with that of the optical signal. So there is a need of the phase locked loop, and you can see that here the phase and frequency of the locally generated carrier should be equal to that of the optical signal. So the phase difference, or in this omega f represents the difference between the phase of received optical signal and the locally generated carrier signal. So omega if will be equal to 0. That means their phases should be equal. That means the difference in phase will be equal to 0. And the amplitude of the signal is ES plus ELO. That means the amplitude of the received signal, and or voltage of the received signal, and ELO is the voltage of the phase locally generated signal. And then it will be given to the photo detector, and once it is detected, or once this optical signal is converted to suitable electrical signal, it will be low pass filtered in order to eliminate the low frequency components. And this is the basic structure of the homodyne receiver. Next we will go to the heterodyne receiver, and The difference of the heterodyne detection from the homodyne detection is that there is no need of the phase locked loop. That is, no need of optical phase locking and frequency matching of local oscillator. That means here omega IF is a non-zero quantity. See, in the case of homodyne detection, omega IF equal to 0. See, there should be a phase locking in the case of homodyne detection. That means omega IF will be equal to 0 in that case. But in the case of heterodyne detection, there is no need of the phase locked loop. That means there is no there will be a phase difference between the received signal. So omega F will be a non-zero quantity, and since there is no need of phase lock loop, the implementation of the heterodyne detectors are easier. But you can see that its performance is degraded performance comparing to the homodyne detectors. And here demodulator circuit is needed, and here once the information is received, information can be transmitted through the different modulation schemes such as ASK, FSK, PSK, like that. And similar to the homodyne detection, the local oscillator power will be very greater than the signal power. And in this case of heterodyne receiver, we can write the receiver output current, which is actually we are writing the DC term of the output current. IDC can be written in terms of the responsibility and incident power. That is, IDC will be equal to responsivity into PLO. That means IDC is equal to eta Q divided by H nu into PLO is local oscillator power. And we can write the in this case, you know that intermediate frequency is a non-zero quantity, so we can write the time varying intermediate frequency current as IF of t is equal to 2 eta Q divided by H nu into root PS into PLO into cos omega IF plus phi of t plus cos theta. You can see that here omega IF is not a non-zero quantity. That is why we are representing this quantity here. And in this case, at the receiver side, this DC terms will be filtered out by the receiver, but the IF, this term, that is the intermediate frequency term, will be get amplified. And in this case, information can be recovered from the amplified current by using conventional RF demodulation schemes. And here, in the case of heterodyne detection, different demodulation schemes is needed, but there is no need of the phase locked loop in the case of heterodyne receiver. Okay. Next, we will go to the sensitivity of the coherent receiver that we have studied in the previous videos. That usually sensitivity is measured in terms of bit error rate. So we have to first know bit error rate. That is BER is the bit error rate, and usually it depends upon the bit error rate depends upon the signal to noise ratio, and receiver sensitivity can be described in terms of the signal to noise ratio available at the receiver output. And this sensitivity is directly signal to noise ratio is directly proportional to the received optical signal power. And receiver sensitivity for the coherent detection scheme is described in terms of average number of photons required to achieve a 10 raised to minus 9 bit error rate. That is important point. In the case of a coherent detector, receiver sensitivity is described in terms of average number of photons required to achieve 10 raised to minus 9 bit error rate. So we will analyze the system for that case. So first we will take the homodyne systems. That means on off key homodyne systems. And in this case, there is two chances what will happen when 0 pulse is received, and what will happen when pulse 1 is received. When a 0 pulse of duration t is received, then the average number of electrons Hall pair is received can be obtained by the relation n0 bar equal to ALO square into t, where this is the local oscillator amplitude, t is the duration of the pulse. For a pulse 1, the average number of electron Hall pairs can be represented as n1 bar. That n1 bar equal to ALO plus AS all square into t. See, when in the case of on off keying, you know that when 0 is received, that means there is no signal. That is why it has got this term. There is only local oscillator signal only. And when one pulse is received, that means there is a presence of the signal. That is why we are taking ALO and AS as here. So ALO plus AS whole square into T, that is equal to ALO square plus 2 ALO into A into T. And once this signal is, after modulation, once this signal is given to the decoder or a photo detector, the voltage V seen by the decoder in the receiver during a pulse 1 is obtained by the relation V equal to N1 bar minus N0 bar, that is equal to ALO AS into T. And the corresponding RMS noise signal at the detector side is equal to sigma square root N1 square. Actually it represents the variance value, that is equal to square root N1 bar, or that is equal to square root N0 bar. And using this we can write the bit error rate as, that is bit error rate will be equal to 1 by 2 into 1 minus ERF, that is error function of V by 2 into square root sigma, that is equal to 1 by 2 ERFC of V by 2 root sigma, that is equal to 1 by 2 ERFC of AS T raised to 1 by 2 divided by root 2, where ARFC of X equal to 1 minus ERF of X, that is error function, and complementary error functions are related by these equations. So the sensitivity is the average number of electrons or photons produced for bit error change of 10 raised to minus 9. So in order to achieve a bit error rate of 10 raised to minus 9, we can write we need a V by sigma value of 12. That means that yields AS square T equal to 36. So thus for an OK homodyne detection, the bit error rate is given by 1 by 2 ERFC of square root eta into NP bar. And this, we can write ERFC of X for X greater than or equal to X 5. ERFC of square root X is equal to e raised to minus X into root pi by X, root pi X. Therefore bit error rate equal to e raised to minus eta NP bar divided by pi n NP bar whole raised to 1 by 2. That means eta NP bar greater than or equal to 5 in the case of OK homodyne detection. And we can say that we can define the sensitivity in terms of the average number of photons received. In the case of OK homodyne detection, we can say that the average number of received photons per bit of information is 36 electron hole pairs. That means the average energy of each pulse must produce 36 electron hole pairs. That means in ideal case, when the quantum efficiency is unity, a 10 raised to minus 9 bit error rate is achieved with a average received optical energy of 36 photons per pulse. So that indirectly indicates the sensitivity. Similarly, we have the PSK homodyne detection. That means if you are using PSK modulation scheme, that indirectly represents the PSK homodyne detection, and in that case AL0 square T will be equal to 9 and bit error rate equal to 1 by 2 into ERFC of square root 2 eta NP bar. That means for an ideal PSK homodyne detection, an average of 9 photons per bit is required to achieve 10 raised to minus 9 bit error rate. That indicates the sensitivity. That's all about this topic. Thank you.